So today we are going to start with Riemann integration. You perhaps already know this as the definite integral. Today we are going to start with the theoretical construction of this integration. It was first done by the German mathematician Bernhard Riemann. That's why this integration is called Riemann integration. Now, historically speaking, the theory of integration precedes the theory of differentiation. It was actually known to the ancient Greeks, and it is essentially their method which Riemann has analytically established. So first we will start with the usual technique of integrating as conceived by the Greeks. It is essentially to find out areas of certain regions in terms of the areas of certain regions which you already know. For example, we know what we mean by area of a triangle. We know what is area of a rectangle. But using this, can we find area, let us say, of a disk? That is what the ancient Greeks have done. So let me explain first that to you in the modern language. So the problem is this. I look at a disk whose radius is r. So this distance is r. Call this disk D. Question is, what is area of D? When we ask this question, surprisingly, it makes sense to everybody that we can try to find the area of the unit of the disk D. But the question is, it has not been defined a priori that what exactly is area of a disk. What is the definition of the area? We will see, we will proceed inductively, intuitively, and see that the Riemann integration actually defines the notion of area for us also. It is not only calculating areas, it defines the area also. So we follow the Greek method, which goes as follows. I draw a bigger picture of the disk, and then this is the center. And what I do is, I look at this triangle where this angle, let us say, is 2 pi by n. That is, I am actually trying to write down this disk as union of triangles where the top angle is 2 pi by n. So I am going to use n many triangles. And obviously, I can see from the picture, it is not going to fill up the whole disk. Some portion will be left. But notice just one thing, that if I take L bigger n, that means L lesser 2 pi by n, then the picture would look something like this. Okay? And then I can go on increasing the n's, and perhaps these triangles which I am drawing, it is getting almost equal to the disk. But we are not satisfied with just this. What I will do is, I will draw another triangle which is slightly bigger. It is this. Okay? So separately the picture looks like, first triangle is this, where the top angle is 2 pi by n, this is 2 pi by n, and there is a slightly bigger triangle with the same angle. I know this side is r, so is this side. And if I draw this line in the picture here, it is this line, I know that this is also r. Up to this is r, up to this is r, and this whole thing is also r. Okay? Now, I want to find the areas of the smaller triangle and the bigger triangle. Okay? Fine. So I will draw another picture of this. Now I write a bigger disk. This is the center. I have this smaller triangle, which is the inscribed one, and then I have a bigger triangle, which is superscribed one. This line I know has length r, this line has length r, this side has length r, and this whole angle is 2 pi by n. Now if I try to find out first the area of the smaller triangle, so let me give a name O, OAB, and the bigger triangle is OA prime B prime. So first try to calculate the area of OAB. What is that area? Well, the half angle in the top is certainly pi by n, and then I know this length is r, that is the hypotenuse. So the area is half times the base. Well, the base is r sine pi by n times the altitude. What is the altitude here? Well, it is just r cos pi by n. Okay, so half times sine pi by n times r cos pi by n. Now, how many such triangles are there? But I have two triangles. So the area of OAB is actually what I have written as half, is actually the half of OAB. So area of OAB is this times 2. So it is r sine pi by n times cosine pi by n. Well, r square. Now, how many such triangles are there? Obviously n many, because I am looking at the angle 2 pi by n, the whole angle is 2 pi. So total area of inscribed triangles is equals to n times r square sine pi by n into cosine pi by n. Now we will concentrate on the area of the bigger triangle, that is O A prime B prime. Let us see what is the area there. I know length of this line r, this is r, that I know, and then I know the angles, those are pi by n's. So again it is half the base into altitude. So let us see area of O A prime B prime, that is equals to 2 into half. In any case I know the altitude here, so it is r into, now the base, well the base is clearly r tan pi by n. So the total area turns out to be, in this case, r square tan pi by n. Then what is the total area of the superscribed triangles? So total area of the superscribed triangles is equals to n times r square tan pi by n. Now let us assume that area of D is equals to alpha. Okay, our intuition suggests that if some such alpha exists, then this should be true, that n r square sine pi by n into cosine pi by n is less or equals to alpha, because I am looking at the left hand side represents the total area of the inscribed triangles. So the total area is certainly smaller than the total area of the disk, so it is less or equals to. On the other hand, this alpha is less or equals to n r square tan pi by n, because now the right hand side represents the superscribed triangles. So the total area must be bigger than the area of D. Now this is true for all n. as I said, that if I go on taking larger and larger n, it looks like the triangles are almost filling up the whole disk. So I want to take the limit as n goes to infinity and see what happens. But whatever the limit is, inside both the limits, the alpha remains, right? Alpha still stands in between both the limits. So once I take the limit, what is this quantity? Limit n going to infinity, n r square sine pi by n times cosine pi by n. I just write it in the form limit n going to infinity, n r square sine pi by n divided by pi by n into pi by n times cosine pi by n. Now these two n's cancel each other. Notice that this portion as n goes to infinity has the limit 1 because pi by n goes to 0 and cos pi by n then goes to 1. So the net result is pi r square. So one thing then is certainly clear, that this implies that pi r square is lesser equals to alpha. Now let us look at the right hand side, that what is this limit? Limit n going to infinity, n r square tan pi by n. Well, I write it in the following form, limit n going to infinity, n r square sine pi by n divided by pi by n into pi by n into 1 by cosine pi by n. As in the previous case, these two n's cancel each other and what I get is pi r square. So this implies now that alpha is lesser equals to pi r square. These two together imply then that alpha is equals to pi r square, which we know is the radius of the disk of, this is the area of the disk of radius r. So this we call the area of D. But there are certain hypotheses we are using tacitly here. Number one, the disk D has something called area, which has not been guaranteed. Second is, this area satisfies some kind of inequalities, that the inscribed triangles had lesser area than disk, which looks bigger, and the disk has lesser area than the superscribed triangles, which looks bigger. This we are assuming. Under these assumptions, which are very natural assumptions, we will like our area to possess these properties. It comes out that area of a disk of radius r is pi r square. So whatever we have done is very ancient mathematics, done before Christ by the Greeks. Now let us see what Riemann did to analytically establish this technique in the present day mathematical framework. So we start with the following. Again, I will first try to informally tell you what exactly is Riemann's idea of doing integration. For that, let us say f is a function on closed interval ab to r. Assume that f is bounded and non-negative. Okay. Let us assume that I can draw the graph of the function f. So these are the axes. This is my interval a, b. Let us say the function looks like, very simple kind of a function I have taken. What I want is, let us draw these vertical lines first. What I want is, I want to find the area between this enclosed region. Okay? I want to find this area. Now notice that it has not been predefined, but as in the disk case, if we follow our intuition, sometime area comes out, so we try to do exactly the same thing here. Okay? So for that I need certain things to define first. First I define something called partition. Partition just means a collection of points x0, x1, x2 and so on up to xn equal to b. That is, it is collection of points between a and b. So what I do is I mark them. Let us say these are the partition points. At these partition points, what I do is I first draw vertical lines until it intersects the graph of the function. I go on doing this at each of the partition points. They look like rectangle, but you can see that one side of the rectangle is not really a straight line, it is a curved line because it is on the function side. Okay? Now I start from this line and draw this, then I draw this, then I draw this, and I go on doing this. You see that I get certain rectangles, but these rectangles are below the function. If I find out the areas of all these rectangles and add them together, what does our intuition say? This added sum of the areas of the rectangles is less than the area of the region below the graph of the function. That is intuitively very clear because rectangles are inscribed inside. Similarly, I can draw some superscribed rectangles also. They are drawn in this fashion. So take the higher point on the curve of the graph of the function and draw the bigger rectangles. And then if I find out the areas of the bigger rectangles and sum them up, it is certainly going to be bigger than the area of the region under the graph of the function. Okay? Fine. Now how do I draw these rectangles? That is the next question. So I define something like this. I define capital Mi equals to supremum of fx when x lies between xi minus 1 and xi. Since the supremum depends on I called it Mi. Similarly, I can define little mi, that is infimum of fx when x lies between xi minus 1 and xi. Notice that if I draw a rectangle whose base is the interval xi minus 1 xi and whose height is little mi, then I get a rectangle which lies below the graph of the function, right? It just touches the function at one point, that is at little mi. If I draw a rectangle with base xi minus 1 xi interval and whose height is capital Mi, then that rectangle goes above the graph of the function. Okay? Now I define UPF equals to summation I from 1 to n capital Mi times delta xi, where delta xi is the length of the base with interval xi minus 1 xi, that is, it is xi minus xi minus 1, and I define LPF equals to summation I from 1 to n little mi times delta xi, where delta xi is same, it is xi minus xi minus 1. From the construction, one thing is very clear. LPF is less or equals to UPF. This is simply because LPF uses the infimums and LPF uses the supremums. Fine. This is it just means, if you notice that what is UPF, it is just sum of areas of the rectangles which superscribe the region under the curve, because each term capital Mi times delta xi is height times base. So it is area of a rectangle, and then I am summing them up. So the partitions actually gives me the base of the rectangles which I am choosing, and then the mi's give me the heights. Then mi times delta xi gives me the area of a single rectangle, and then I sum them up over all the base which I have chosen. Similarly, LPFs. Now comes the next observation, which is again clear from the picture. Let us again draw the picture of the function which I had taken earlier. This is A, this is B. My function looked something like this. Suppose I mark the partition points as earlier. Now I add some extra point. Let us say here. I choose another point x star. Okay. So my original LPF rectangle was this. This was my original rectangle. Now if I assume that x star is also a point of the same partition, let's assume that, then I should have done this. I should have drawn this line and then this line. So the earlier rectangle which I was working with, it is this. And now the new rectangle which I am getting, it looks exactly like this. You can very easily see now that by putting an extra point, what I have achieved is that the new rectangles which I am getting, they are giving a bigger area. So mathematically, what I drawn so far can be explained in the following. I first define something called refinement of a partition. Let P1 and P2 be partitions of AB. Then P2 is called a refinement of P1 if P1 is a subset of P2. It means what? It just means that given the partition P1, I have inserted some more points in the partition to create P2. So P2 is actually breaking the interval in a more refined fashion than P1. That's why it is called the refinement of P1. So one thing is very clear from this definition, that P2, after all, any partition is a collection of points. So P1 is also a collection of points, so is P2. But P2 has more points in it than P1 as a set, not just number of points. All points which appear in P1, they also appear in P2, but P2 has more points perhaps. That's why P2 is called refinement. Now the basic question which we are going to ask ourselves, that given any partition P, I can talk about LPF. So I can talk about LP1F, I can also talk about LP2F. These are two numbers. what is the connection among these two numbers? Which one is bigger? If you look at the picture, then perhaps you can guess that LP2F is bigger than or equals to LP1F, because you are putting more points there, so the rectangles are gaining height, so the total area will be bigger. So let us try to prove it analytically. So this is our first theorem. If P1 and P2 are partitions of AB such that P2 is a refinement of P1, then LP1F, and for UPFs the total relation actually changes, that UP2F is less or equals to UP1F. So now I want to prove this. In the proof, I will just assume that P2 has only one more point than P1, because then one can inductively proceed with the same argument. With 1 point more, if you can prove the result, certainly I can prove the result with 2 points more, and so on. So assume that P2 has one more point than P1. Let us say the point is x star, and it appears, well, let us assume that P1 equals to x0, x1 up to xn, and P2 is xi minus 1, then the additional point x star, then xi, then up to xn. So what P2 actually looks like, that if you look at the points xi minus 1 and xi which appears in P1, then there is an additional extra point x star between those two, which is there in P2 but not in P1. So P2 has exactly one more point than P1, and that point is x star. Now we are trying to calculate the LPFs first. The proof for UPF is analogous. Now what I am interested first in is this set infimum fx, where x lies between xi minus 1 and x star. I call this W1. Similarly, I can look at infimum of fx where x belongs to x star xi plus 1, this interval, x star xi. I call this W2. Now observe one thing. If mi equals to infimum of fx when x belongs to xi minus 1 xi, then W1 is bigger than or equals to mi, W2 is also bigger than or equals to mi. Why is so? Because infimum of a smaller set is always bigger than the infimum of the bigger set. The set fx x in xi minus 1 xi is certainly bigger than the set all fx such that x is in xi minus 1 x star, because x star is less than xi. Okay, so that is a smaller set. So in that smaller set, if I look at the infimum, that is certainly bigger than the infimum of the much bigger set. That's why I get the inequalities that W1 and W2 both are bigger than or equals to Mi. Now I look at this quantity LP2F minus LP1F. So I just write them down. Remember that there is difference of only 1 point in P2 than in P1. So I can write summation j from 1 to I minus 1. First this, I will write this as mj delta xj plus W1 times x star minus xi minus 1 plus W2 xi minus x star plus summation j from I to n mj delta xj. Okay, this is LP2F. Now comes minus LP1F, that is summation j from 1 to I minus 1 mj delta xj plus mi delta xi plus summation j from I plus 1 to n mj delta xj. I have just written down the definition of LP1F and LP2F. Now if I compare, I see that all the terms cancel each other, and what remains is W1 times x star minus xi minus 1 plus W2 times xi minus x star minus mi times xi minus xi minus 1. Okay. So what I have done is, it looks so complicated, I have just concentrated on the ith term in the sum of LP2F and have broken it, written it in terms of x star. And while looking at LP1F, I have just separately written down the ith term. All the terms I have kept in, other terms I have kept in the summation. And then you can see that because of the cancellation, only those ith interval is going to matter, others are cancelling themselves. Well, the final step then is, I can write this as W1 times x star minus xi minus 1 minus mi times x star minus xi minus 1 plus W2 times xi minus x star minus mi times xi minus x star. So what I have done is, when I look at the quantity mi times xi minus 1, this xi minus 1 I am just writing as x star minus xi minus 1 and then xi minus x star. And then since I know that W1 is bigger than mi and W2 is also bigger than mi, I get that this quantity is bigger than or equals to 0. That settles the case, because that means then LP2F is bigger than or equals to LP1F. Now if I look at the UPF, what do you think will happen? The only difference is observed in the following relation, that if I define V1 to be equals to supremum of fx when x belongs to x star xi minus 1 and V2 equals to supremum fx when x belongs to xi x star, and I define capital Mi equals to supremum of fx when x belongs to xi minus 1 xi. Then what is the connection between V1, V2 and Mi? Because while dealing with LPF, I dealt with the connection between W1, W2 and little mi. So analogously, I have to deal with V1, V2 and capital Mi here. Well, here the obvious thing is that supremum of a smaller set is always smaller than the supremum of the bigger set. This implies that V1 is lesser equals to Mi and V2 is also lesser equals to Mi. This then would imply, just exactly as in the previous case, that UP2F is lesser equals to UP1F. Again, I can explain it by pictures. The case of UPFs, I have A here, I have B here, I draw the graph of the function as this. I look at these two partition points, then the corresponding bigger rectangle I have to draw because I am dealing with UPFs now. The bigger rectangle is this. I draw the same picture again here just to show you the difference. These are the 2 points. Suppose there is a partition point inside. Draw the graph of the same function. Then I have to draw 3 vertical lines. 1, 2, this is the third one. And I am drawing the bigger rectangles. This is the first one, this is the second one. Now you can compare. In one case, I had this rectangle. In the next case, what I am getting is, go back to the picture, you see what I am getting. Compare it with the previous page. This was my first rectangle without the partition points. Then what I get is this one. This fellow certainly has a smaller height. See the next page. The first one is of the smaller height. That means this area is certainly less. This is what is actually explained by saying that if I look at the refinement of partitions, then UPFs are actually getting smaller. Now let us notice the following thing, that since I have assumed that f to be bounded, since f is a bounded function, there exists capital M and little m such that capital M is bigger than or equals to fx is lesser equals to little m. This capital M is actually the supremum of fx. This is supremum of fx, x belongs to AB, and little m equals to infimum of fx, x belongs to AB. Notice then that this implies that capital M into B minus A is always bigger than or equals to UPF, and it is bigger than or equals to m into b minus a. Similarly, capital M into b minus a is bigger than or equals to LPF is bigger than or equals to little mb minus a. This follows from the fact that capital Mi is always lesser equals to m and little mi is always bigger than or equals to little m. Okay. Now, so this would then imply that capital M into b minus a is bigger than or equals to UPF, which I anyway know is bigger than or equals to LPF, but LPF, which is constructed out of mi's, is certainly bigger than or equals to m into b minus a. This is how we get this, which is going to be very fundamental for us, because now I am going to define something called upper Riemann sum. It is denoted as integral a to b bar fx dx. It is just a symbol. The meaning of this is, so this is definition. This is infimum of all the UPFs, because if I go on varying the partitions P, I get different UPFs, and I have already noticed that this set of UPFs, it is bounded by little m into b minus a and capital M into b minus a, so it has an infimum. That infimum I define as the upper Riemann sum, which is, the symbol is a to b bar fx dx. Similarly, I define lower Riemann sum, which I denote by integral a bar to b fx dx. Notice that right now this dx has absolutely no meaning. The meaning of this symbol is explained by, this is supremum over all p LPF. That is, I construct in UPFs and then I look at their infimum. I construct LPFs and I look at their supremum. Because again, if you think back at the picture, as I go on taking finer and finer partitions, UPFs are coming down. So finally they are supposed to collide with something, and that thing is the infimum. Similarly for LPFs, as I go on taking the refinements of the partitions, LPFs are increasing. So they will collide with something. That thing is the supremum, which is the lower Riemann sum. Now a function f, this is the definition. A function f which is certainly bounded. Notice that boundedness is very important, otherwise capital Mi and little mi's will not exist. For the existence of the supremums and infimums, I need boundedness of the function, is called Riemann integrable over AB if the lower Riemann sum is same as the upper Riemann sum. That is, if a to b bar fx dx is same as integral a bar to b fx dx. And in this case, we define the Riemann integration of f as integral a to b fx dx, which is the common value of the upper Riemann sum and the lower Riemann sum, that is so the whole process is again this, that I look at all possible partitions of the closed interval AB. Corresponding to each partition, I look at UPFs, I collect those UPFs, look at the infimum of that set. Then corresponding to each partition, I look at the LPFs, I look at that set, I look at the supremum. If the supremum and the infimum are same, then the function is called Riemann integrable, and the Riemann integral of the function is defined to be that supremum. It is same as that infimum, because the definition of Riemann integrability demands that the supremum and infimum are same. Now, in general, what is the connection between the upper Riemann sum and the lower Riemann sum? That will be needed in the sequel, so I just include it as a lemma. In general, what we know is that integral a bar to b fx dx, this is the lower Riemann sum, it is always less than or equals to integral a to b bar fx dx. In general, this is the relation between the upper Riemann sum and the lower Riemann sum. When these two quantities are same, then the function is Riemann integrable. Now, how to prove this? Well, I take any partition P1 and P2 of AB, and P is the common refinement of P1 and P2, means P is just P1 union P2, that is then another partition. Then I anyway know that LP1F is less or equals to LPF. As I have observed, if you put more points in a partition, then LPFs increase. But LPF is anyway less or equals to UPF, but P has more points than P2, so UPF is less or equals to UP2F. Now what I do is fix P2. Then supremum over P1 LP1F, that is certainly less or equals to UP2F, because the above inequality is true for all P1 and P2. But this then implies that integral a bar to b fx dx, which is by definition the supremum of all the LPFs, is less or equals to UP2F. This is true for all P2. This then implies that integral a bar to b fx dx is less or equals to infimum over P2 UP2F. But this is by definition a to b bar fx dx. So the relation is proved. Now I will just give you an example to show that not every bounded function is Riemann integrable. Consider the function f from 0, 1 to r given by fx equals to 1 if x is rational, equal to 0 if x is irrational. It is very easy to see that this function is not Riemann integrable, simply because the following: take any partition P any partition of 0, 1. Then my question is, what is UPF? Well, this is summation I capital Mi delta xi. But if you take any subinterval of xi minus 1 xi, there will be some rational point there, and at other irrational points f is 0, but at the rational point f is 1. So the supremum is 1, that means capital Mi is 1 for all I. That means it is just summation over I delta xi. That is the length of the interval, which is 1. Now if I look at LPF, that is summation over I little mi times delta xi. What is little mi? Little mi is the infimum of the function over a ith subinterval. Well, fix any I, look at the subinterval xi minus 1 xi, it will certainly contain an irrational number, but then f is 0 there. That means in all the subintervals, the infimum of the function is 0. That means little mi is 0 for all I. That means the final sum is 0. Now if you take supreme over all partitions P, that means the upper Riemann sum, that is 1. This implies the upper Riemann sum is 1. But for all partitions P, LPF is 0. That means the supremum of the LPFs, that is also 0. That means the lower Riemann sum is 0, which is not equal to the upper Riemann sum, and hence the function is not integrable. So there exist functions which are not integrable. So the next question which we would like to ask is, well, what are good examples of integrable functions? That is, what are Riemann integrable functions? Do we have examples of large class of functions which are Riemann integrable? For example, continuous functions, differentiable functions, are they Riemann integrable? The so-called good functions should be Riemann integrable. So that is the next thing we are going to examine. So in the next lecture, we will continue with our investigation of finding examples of large class of Riemann integrable functions. But the problem there is, we need a criteria to determine when a function is Riemann integrable. What we have so far is just the abstract definition of Riemann integration. It turns out that with this definition, it is difficult to show that certain functions are integrable. Just like if you look at sequences, just the definition of convergence of sequence is not good enough to check whether a sequence actually converges. Similarly here, we need a necessary sufficient condition which one can handle to use to check whether certain functions are Riemann integrable. That is the next thing we are going to do in the next lecture.